Welcome, welcome. We have lately been looking at different types of functions, and today we're going to look at our first limit, which is an idea from calculus. So we are transitioning from review into calculus ideas. And we're going to focus on one example so we can really look at it thoroughly. So let's look at this example. Suppose that a ball is dropped from the upper observation deck of the CN Tower in Toronto, 450 meters above the ground. The distance it has fallen after t seconds is given by the equation S of t equals 4.9 t squared, where S is given in meters. Find the velocity of the ball after 5 seconds. Now, this is not S times t. This is S, the distance, as a function of t. Oftentimes, we use the letter S to represent a distance function. I'm not exactly sure why S. I believe it actually goes back to something in German. But regardless, this is a distance function. And what we're wanting to find is the velocity after 5 seconds. We want to find the velocity at a very specific moment in time, at a certain instant. And I want to be clear here, this is different from the average velocity over a certain interval of time. If we want to find the average velocity, that is a lot simpler. To find the average velocity over a certain time period, all we need to do is take the change in position and divide it by how much time has elapsed. If you drove 180 miles, that's your change in position, over 3 hours, then you take 180 divided by 3 and you get 60 miles an hour. That's your average velocity over the course of that time. So let's do an example of that for this particular problem. Let's look specifically at the time interval from 5 seconds to 10 seconds. Let me show you how we would calculate that average velocity. I'm going to use V sub AVE for average velocity. That would be the change in position. So the ending position is going to be the position at time 10 minus the starting position, which is the position at time 5. Remember, S is the position function, over how much time has elapsed. And we can figure that out by taking the difference in the ending and starting times, 10 minus 5. Now in the numerator, we'll have to actually plug in for those functions. S of 10 is 4.9 times 10 squared. Minus S of 5 is 4.9 times 5 squared, all over 10 minus 5, which is 5. And you can just plug that into a calculator. You will end up with 73.5. And this is a velocity. It's going to be in meters per second, since our distance was measured in meters and our time was measured in seconds. So this is an example of how we can use this formula when we're given a position function to figure out the average velocity over an interval of time. Now, unfortunately, this is going to be way off for the instantaneous velocity. If you think about what's going on, we're dropping a ball from the top of a tower. Gravity is acting upon it, and so it's going to be getting faster and faster and faster. So even at 6 seconds, it's going to be faster than it's moving at 5 seconds. So if we're considering the interval all the way up to 10 seconds, basically throughout this whole interval, it's going to be moving faster than it was at the very start of the interval. So this is going to be very much an overcalculation. If we want to get a better estimate, what we could do is look at a shorter interval. There's actually several things we can do, but I want to look at a shorter interval. Let's look at just a 1 second interval. Let's look at the time between 5 and 6 seconds. Again, we can calculate the average velocity by taking the change in position, so that'll be the position after 6 seconds minus the position after 5 seconds, over the change in time, 6 minus 5 seconds, which in the end is just 1. And so we've got our s of 6, so that'll be 4.9 times 6 squared, minus s of 5, which will be 4.9 times 5 squared. And again, to save time, I'm going to use a calculator. This is going to give us 53.9 meters per second. Now, we mentioned that the first calculation we did was going to be too large of a number because between 5 seconds and 10 seconds, it speeds up quite a bit. Our new approximation is lower, which is what we would expect, but this is still going to be an over approximation, an overestimate, because it includes everything in the interval between 5 seconds and 6 seconds. And of course, throughout that interval, it is getting faster in each moment between second 5 and second 6. So we're still overestimating a little bit. Now, we can't do the interval from 5 seconds to 5 seconds. That is not a calculation we can do, because if we were to try to do that calculation, we would end up with the same thing in the 2 terms in the numerator and the same thing with the 2 in the denominator, and we would have 0 over 0, which is undefined. So we can never use this formula on an interval that's only really 1 point. But what we can do is we can take smaller and smaller intervals. We could go from 5 seconds to 5.1 seconds. We could go from 5 seconds to 5.01 seconds. We could even go to 5.001 if we wanted. And what's going to happen is we're going to be getting answers that are getting closer and closer to the real answer, the real instantaneous velocity. In fact, I have already gone through and done these calculations. Let me show you what they are in a little table. All right. This table has the calculation we just did from 5 seconds to 6 seconds, 53.9 meters per second. If we look between 5 seconds and 5.1 seconds, 49.49, and we've got a few more smaller and smaller intervals, all the way down to this interval between 5 and 5.001 seconds. And if you look at the answers that we're getting, the average velocities, as we take this interval to be smaller and smaller and smaller, you can see that these numbers are getting smaller, and it looks like they're getting closer and closer to a very specific number, right? If you look at these 4, all of them are above 49, but they're getting closer and closer and closer to 49. And if we were to look at the next one, 5.00001, we would end up with 49.00049. Basically, these are getting closer and closer to 49 meters per second. And in fact, that is the instantaneous velocity at 5 seconds. It is 49 meters per second. And we call this a limit because what we're doing, we can't actually look at an interval that has no width, but we can look at intervals that have shorter and shorter and shorter widths that are getting closer and closer to just looking at the instantaneous moment at 5 seconds. And if we look at what happens to those velocities, they are getting closer and closer to 49. And in the end, we can conclude that that is the instantaneous velocity. We are going to continue to look at this specific problem in a slightly different way in the next video. We're going to look at things graphically so you can see another way that we are considering this as a limit. And just a notice, kind of a look ahead, we're going to be spending many of the next several lessons looking at limits, getting to understand what they mean a little bit better, looking at different ways to calculate limits. This is a big part of calculus, and you've just seen it a little tiny bit for the first time, but we will be diving in deeper to this and getting a more thorough understanding of limits.